Start with them? Okay. Good afternoon, one and all. I am Manish Mesuria, Assistant Professor in Mechanical Engineering Department, Parul Institute of Technology, Parul University. We are gathered over here for learning and understanding a promising topic. So, topic is on the effect of the parameter on the geometry accuracy and the surface roughness of the component formed using a multi-stage increment sheet forming process. So now I would like to introduce our resource person, Mr. Sunan Gajja. Sir had completed his masters from the SVNIT Surat, and sir is completed. Is qualified is GATE 2019, and with good score also. Sir is working in as a design engineer in Armstrong Electronics Private Limited at Baroda. Sir have a 1 year teaching experience and 2 years in industrial experience in field of the design. Now I would like to request sir to start our session. Sunan sir, please.
So, hello everyone. So today's webinar is on based on multi-stage incremental seed forming. So we go through the slide. 1 minute. Manisha, is it visible?
Yes, sir. Completely visible.
Okay. Okay. So let us start. So today's webinar is based on multi-stage incremental seed forming. So I'll quickly go through the couple of slides before starting the effect of parameters on geometric accuracy and surface roughness. Okay, so first of all we learn about the what is incremental sheet forming process. Here is the principle of sheet metal incremental forming. And also here, before we go through the incremental sheet forming, we can uh, go through some basic fundamentals of sheet forming. Okay, then subsequently we will discuss on the effect of parameters and what are our findings. But first of all, we learn about the seed forming. What is seed forming process? Okay. So in the forming process, the forces are applied. Uh, gr- the forces are applied greater than yield strength, right? As you know about the stress strain diagram. Okay. I hope all are aware about the stress strain diagram. So there is ultimate strength and yield strength. So ultimate strength hello, hello,
Yes, sir. Yes, sir.
am I audible?
Yes, sir. Yes, sir.
Okay,
You are audible.
okay. So in seed forming, we worked between yield strength and ultimate strength. Means we can say plastic deformation zone. Okay. So these stresses are here induced. It is greater than yield and less than ultimate. So the shape will change and no fracture will be observed. Okay, because if we go beyond ultimate strength, so the fracture will be observed. Okay, but we are not going beyond the ultimate. We are going uh, between yield strength and ultimate strength. Okay, so the shape is all only change. uh, there are various operations in sheet metal, like like punching, blanking, deep drawing, okay, bending. There are also other operations like nibbling, perforating, and all. But here, punching and blanking, the stresses are induced are greater than ultimate strength, okay, because they are cutting off processes, okay. Punching, blanking, you are aware about the punching and blanking operations, right? So in these operations, the stresses are induced greater than ultimate strength, okay. So that is why they are known as cutting processes, okay. But in deep drawing bending operations, the forces are greater than yield strength and less than ultimate strength. So they are known as forming processes. And we have seen a lot of utensils in our kitchen which are formed using deep drawing processes, okay. But what happened, here I explain you the deep drawing process, okay. So why we introduce this incremental seed forming? Before that we have to learn about the deep drawing process, okay. So I quickly start this incremental seed forming process. But before, why we use this incremental seed forming? So before that we have to learn about the deep drawing process, okay. So in deep drawing process, the punch and die setup is used, right? uh, and because of the punch and die setup, we require the we have to design the punch and die also. So that will increase the cost. But here incremental seed forming, there is no die setup is used, okay. No punch setup, no die setup is used. Here is only the forming tool is used, and between two plates the seat is kept between two plates only, okay. So though no die setup is used, so that will decrease the cost. And also in deep drawing processes, we cannot make the we cannot produce the required size and shape of component directly. Means we cannot because it require higher force, okay. If we directly produce require size and shape of component, then we need higher force, okay, by the punch. So that will lead some localized cracking, and also that will taking place. So to avoid this localized cracking, deep drawing is always carried out using multiple stages, okay, or we can say multiple draws, okay, multiple stages or multiple draws. So in each and every stage, a separate punch and die combination is used, okay. Every In every stage we have to use separate means different punch and die setup. So we need to design for every stage punch and die, okay. So here the seed forming, incremental seed forming can be beneficial, but the limitation is we cannot use for mass production. For mass production, deep drawing process is okay, but for small batch production we can use this incremental seed forming, okay. So here is the figure shows the principle of incremental seed forming, okay. The forming tool, I think the pointer can be visible. Manish sir, is the pointer is visible?
Yes, sir. Yes, sir. It's
Okay.
visible, sir.
Okay. So here is the forming tool. Okay. In deep drawing process, the punch is used, but here we can form the required shape of component using the forming tool. So the forming tool will travels along the predefined tool path. Okay. And using a number of incremental yes, yes, this is the delta z, right? Delta z. So this is the, so we can say pitch size, okay, incremental, depth incremental, okay. So the tool, uh, the farming tool will travel along our predefined tool path, okay, and also in z direction using small incremental pitch sizes, delta z, okay. And this is the theta, this is the wall angle, okay. So these are the important process parameters. Uh, the tool diameter, the step size, delta z, wall angle. Okay, so these are all the important parameters which are affects the formability of seed forming. Okay, so we'll discuss these parameters later on. But first of all, we learn about this principle of sheet metal incremental forming. Okay, here we can also observe the formability which incremental sheet forming have better than deep drawing process. And these are the major applications. We can using the incremental sheet forming, we can make rapid prototypes easily. Then automotive applications, then non-automotive applications, and medical applications. Here we can generate the complex shapes, which we can say for cranial plate, dental plates, there are the complex shapes, right? So we can generate these shapes easily using incremental sheet forming. Okay, so automotive applications, reflexive surface for headlights, vibration, heat vibration shield, silencer housing for truck, and non-automotive motorbike seat, motorbike gas tank, solar oven, production die, mold surfaces that, and medical applications, cranial plate, dental plate. So we can make complexes easily using incremental sheet forming, because if we use the deep drawing process, right, so we have to design the die setup, we have to design the die and punch and all. But here there is no die and punch is used, so we can easily generate these complex shapes using incremental sheet forming. Here we the sine law is presented. Actually, this incremental sheet forming has the limitation. We cannot generate 90-degree wall angle. Okay, here we can say this alpha is the wall angle, right? The alpha, you can see the alpha is wall angle. So alpha cannot be 90-degree. If we if we go near or 90-degree wall angle, the material will be fail. Okay, the component will fail, because there is one sine law from the experiments. This sine law is observed. It is an empirical relation. uh, T final, this is the T final, means final thickness of the sheet, and this is final thickness of the component. Okay, and this is the Ti, initial thickness of the sheet, right? So there is an empirical relation between thickness of sheet and wall angle. So T final is equal to T initial into sine 90-degree, sine of 90 minus alpha. So if we keep the value alpha is 90-degree, then sine 90 minus 90, so sine 0, then T final will lead to zero thickness of the part. So that is why we cannot use 90-degree wall angle. Okay, so this is the limitation of the incremental sheet forming. And then we introduce the multi-stage incremental forming. Using multi-stage incremental forming, we can obtain the 90-degree wall angle also. Here incremental forming, 90-degree wall angle cannot be formed, but using multi-stage incremental forming, we can obtain the 90-degree wall angle. So here you can see stage by stage. First of all, H1, then Hi, then Hn. Okay, so we cannot form directly uh, required shape and size, right? If we required height is Hn and required wall angle is alpha n, then we cannot directly meet that required shape and size. We go some intermediate shapes. Okay, like first of all we go through h1 height and alpha 1 wall angle, then uh, height hi and wall angle alpha I, and then uh, there are we cannot say 3 stages, 2 stages. it depends on the size of the component and require wall angle. Okay, so we can use the 3 number of stages, 4 number of stages, 5 number of stages. Okay, so based on the require size, require height of the component and require wall angle of the component, we can decide the number of stages. These are the multi-stage incremental forming strategies. First is incremental diameter, second one is incremental draw angle, and third is incremental part height and draw angle. Here in first figure we can say we can observe incremental part diameter, right? So first the diameter d1, then di, and then dn. Okay, so first we will form d1 diameter. Okay, the final required diameter is dn. Okay, but we go through some intermediate shapes. Okay, so first d1, then di, and then dn. Okay, so the backing plate is fixed between blank holder and the plate. Okay, and then intermediate shapes we can uh, observe some intermediate shapes d1, di, and dn. Okay, second one is incremental part draw angle. Second one is incremental part draw angle. So there are alpha 1, alpha I, and alpha n wall angle. Okay, so in first figure we increase the diameter only. Okay, we only increase the diameter in each stage. But in second figure we increase the wall angle. Okay, we increase the wall angle alpha 1, alpha I, alpha n. Suppose 30 degree, 40 degree, 50 degree. Okay, then in third figure incremental part height and draw angle. So we simultaneously increase part height and as well as the draw angle also. So if we say h1 20 centimeter, then alpha 1 20 degree wall angle, then we can observe 40 centimeter 40 degree wall angle, and that's all. So the here in third figure both are increasing, right? Part height and draw angle. In first figure only part diameter is increased, second figure the wall angle is increased, and third figure part height and draw angle both are increasing. This is geometric inaccuracy. Actually this what is geometric accuracy? So if we observe some differences between the target profile, okay, means we can say design profile, okay, and after forming what is the profile of the component. So in between this profile if there is some difference, so that is called a geometric inaccuracy. But why this geometric errors occur in this incremental seed forming process? So because of these some reasons, seed bending, pillow effect, seed spring back, this geometric inaccuracy occurs, right? So we cannot get the required shape and size of the component as we cannot get the required dimensions, or we can say required height of the product, or we can say part, after the forming process because of this seat bending, pillow effect, and seat spring back issues. So there is also one clamped inaccuracy, or we can say clamped accuracy. So if we the part is clamped between two plates, then the accuracy of the part is different. And when we unclamp the part, then the observed accuracy is different than the clamped accuracy. Why this unclamped accuracy means why the shape is changed after unclamp the part? Because the residual stresses are generated when we unclamp the part from the fixture, right? So because of the residual stresses there is some inaccuracy we can observe on the geometric shape. Here the seat bending is also observed near the major base of the part. Okay, up, we can say here seat bending, which is near to the this blank holder plate, right? And here the pillow effect is also observed. uh, Pillow effect means at the center, the shape is different than the ends, right? So this is the pillow effect, and this is the seat spring back, because of the materials and also because of the tool. And if we distract the tool, or we can say we can if we unclamp the system, then this seat spring backs are occurs. So because of this, the inaccuracy we can observe in our part. These are the spring back effect. Okay, there are four components. Means first we can say local deformation during forming process. Because of these reasons, the spring back of the form parts will be observed. Okay, so first of all, during the forming process, there is the local deformation observed. Then we can say after unloading the forming tool, when the tool is retracted to its original position, then the spring back can be occur. And when the form part will release from the clamp devices, then also the spring back effect is all observed. And after trimming process, this spring back will also observe. Trimming process means when we cut the parts in required shape and size, the spring back will be occur. Means we can say we will remove unwanted material from the part, then this spring back will be occur. Here form parts are we can observe from the clamps when they are releasing from the clamps. Okay, so first one is the pyramid shape. First one is pyramid shape, and second one is cone shape. Okay, first one is pyramid and second one is cone. So here we can say, here we can directly observe the profile is not proper, right? The profile is not proper around the all edges. Okay, around the all edges, we can observe the profile is not clear. So these are the geometric inaccuracies are occur. Uh, as a design engineer, you have to you have some knowledge of all these processes, like sheet metal forming, then we can say welding, then we can say injection molding. Okay, and if we have brief knowledge about all these processes, and all also after the forming or after the cutting, which are the defects are observed. Okay, which are the defects are observed on the part. If we have this knowledge, and also if we can, if we have some remedies, like if we have some uh, solutions, so what method we can eliminate these defects, then we can obtain our required shape and size, or our required quality of the product, right? So as an engineer, you have to you have some knowledge about the basic processes and also their defects. Okay, how to which defects can be arise from the processes, and also how to remove their these defects, right? So if we have some knowledge about this process and all, so you can easily communicate to your supplier, right? You can easily communicate to your supplier. So uh, the final product, we will get the final product with no defects and required quality. uh, Here also this spring back effect observed in Abacus software. This Abacus software is the simulation software from Dassault. Uh, Actually, the SolidWorks and Abacus both are from Dassault system, Dassault software. Okay, so here you can see when the tool is at bottommost position. Okay, when the tool is at bottommost position in the part. Okay, so here the one graph is shown between displacement versus true distance along path. Okay, this is the displacement These are the values: 2 unit, 4 unit, 6 unit. So this is a displacement, right? Means we can say in z direction, okay, in vertical z direction. And this is the true distance along with the path, okay, true distance along the path. And this graph is when the tool at topmost position, or we can say when the tool is retracted from its position, right? Or we can say to its original position, right? So here we can observe both charts are different, right? When the tool is at bottommost position, and when the tool is at restricted position, or we can say topmost position, right? So we can observe both the graphs are different, right? Here uh, near zero, the displacement value is 10 unit, right? More than 10 unit. But here near zero, near origin, displacement value it's 9 units, right? Yes, this is the 9 units, right? Here also, when the true distance along the path has 10 units, the displacement we can observe near to 4.5, near to 5 or 6, right? But here at the 10 unit true distance along the path, the displacement we observe less than 5, right? Or we can say near to 4. Means both, here we observe both geometry, or both path of the part are different, right? When tool is at topmost position, and when the tool is topmost position. So here one reason is written after unloading spring back effect. Second one is after unloading the forming tool, right? If we unload the forming tool, the spring back effect will be observed in this Abacus software, right? So we learned some limitations, right? 90-degree wall angle cannot be formed, okay. And what are the effects of these process parameters on the geometric accuracy and surface roughness, right? Surface roughness, here the surface roughness we can say the irregularities, right? जो वर्कपीस जो भी फॉर्म होता है उसमें जो irregularities आपको ऑब्जर्व होती है, right? That is called surface roughness. If these irregularities are larger, right? If these irregularities are larger, then we can say the surface is too rough, right? Or we can say the surface is rough. And if these irregularities are smaller, then we can say the surface is smooth, okay. So we here the target means final, uh, we we observe, we have to observe geometric accuracy and surface roughness by using input parameters like these process parameters, or we can say feed rate, number of stages, wall angle, and all, okay. So this objective of the present work is to study influence of process parameters on geometric accuracy and surface roughness in multi-stage incremental sheet forming, okay. Why we use multi-stage incremental? To achieve 90-degree wall angle and also to achieve better accuracy, okay. How we can gain the better accuracy, then we'll learn after some time, okay, after some slides, okay, how to get the better accuracy using multi-stage, okay. So study the influence of process parameters, okay. We have to learn about the influence of process parameters on geometric accuracy and surface roughness. And second one is to develop predictive model for geometric accuracy and surface roughness. We also develop one predictive model for geometric accuracy and surface roughness, okay. There is equations are will be formed for geometric accuracy and surface roughness using input parameters. So this is the experimental plan. First is the design of experiments and selection of process parameters. So this is the experimental plan, means what we have to do in this present work, right? So first of all, we have to do DOE, right? Design of experiments, and selection of process parameters, right? Which process parameters we have to observe, okay? What are their levels, okay? So that's all that That's all will be done using Minitab software. Okay, now using Minitab software, this DOE, design of experiments, will be done using Taguchi method. Okay, we will learn after this slide. Okay, so this, first of all, we have to do design of experiments and selection of process parameters, then forming of aluminum sheet. uh, Here we use the aluminum sheet AL1080 material, which have 1.2 thickness. So forming of aluminum sheet using multi-stage incremental forming, then measurement of geometric accuracy and surface roughness. Okay, then we'll uh, measure the geometric accuracy and surface roughness using some instruments, right? The surf tester will be used for surface roughness, and one scanner and SolidWorks software is used to measure the geometric accuracy. That will also discuss after this slide. Then after the measurement of these outputs, geometric accuracy and surface roughness, then we'll investigate this influence of process parameters, right? Which we have selected. So that influence of process parameters will investigated. Then development of predictive model, okay, of geometric accuracy and surface roughness. So then we'll develop a predictive model using Minitab software. So in that we'll obtain some equations for the geometric accuracy, surface roughness, using some giving by input parameters. Okay, so this is the experimental plan. This is the experimental setup. This setup is used in workshop at SNIT Surat. This is a 3-axis CNC vertical milling machine. This is the fixture, and this is the forming tool. We have to design properly of the fixture, so the setup time can be reduced, and also we can what we can say huh, to improve the seat utilization, right? We can improve the seat utilization. So we have to design a fixture that they so that the least setup time is required, and also we can improve the seat utilization, right? This forming tool is the material for forming tool is HSS an M2 grade, and it has the hemispherical shape. Okay, here you can see the shape is hemispherical. Okay, then uh, the tool path. Okay, here is the tool path. The tool path is taken from the MATLAB programming. Okay, the tool path can be obtained from the MATLAB programming. Some students has done programming on in the MATLAB software. So by giving some inputs, right, like giving the shape we can say cone shape or pyramid shape, then base diameter, means the base diameter, what we can say the bottom. Okay, the bottom at the bottom face, what is the diameter. So the base diameter, step size and height of the object. Okay, so by giving these inputs, step size, you can, okay, so this is the delta z. Okay, delta z is the step size. Okay, or we can say pitch size. Okay, so this is the pitch size. So after giving these parameters on the MATLAB software, we can taken the whole CNC tool path, right? So using this tool path, if using yes, this is the cut viewer mill software. Okay, cut viewer mill software, you using by taken the toolpath from the MATLAB software. If we fed in this simulation software, we can simulate the whole CNC whole the toolpath. Okay, so after simulating the in the cut viewer mill software, we can fed this part program into CNC milling machine, right? Here also you can see the line is observed, right, in toolpath. Actually, there are two types of the tool. Here there are the two parts of the tool traveling, right. First one is in this the tool is moves around the circular, then in step down in z direction, then further it's all moves around the circle, and then further step down. Okay, but using spiral shape, the tool will move around the circle and as well as the vertically downward direction, right, like the spiral shape. Okay, so using this shape, the line is also observed in on our part, right. That will also we can observe after 2 3 slides in the form part. So these are the forming stages and wall angles. Actually, the experiment is done in single stage, then two stage, and then three stage. Okay, so what are the what is the influence of these forming stages on the geometric accuracy and surface roughness? We can observe, right. So one of the process parameter is the number of forming one of the other process parameter is forming stages. So first is single stage, then two stage, and then three stages. So in single stage, means we can say directly only incremental forming, no multi-stage incremental forming, right. Because when we can say multi-stage, if we use greater than one stage, okay, so we can say multi-stage, but here only single stage, so single point incremental forming we can say. So here is only single stage, means 70-degree wall angle, right. So our required part and required part shape and size, means we can say required dimensions of the final part is 70 70-degree wall angle and 45 height, right. So in single stage, here we can observe the diameter will be 110 and 40-degree wall angle and 25 height, right. uh, so if we use single stage, this is the single stage 70-degree wall angle, then that we form the part directly using third stage, means we can say directly we get the 45 height and 70-degree wall angle, right. And if we use two stages, okay, if we use number of stages 2, then first we got the 55-degree wall angle and then 70-degree wall angle, and using 55-degree wall angle 35 height we can get, and using 70-degree wall angle 45 height we can get, right. And using three stages, if we go through three stages, then first is 40-degree wall angle, then 55-degree wall angle, then 70-degree wall angle, and with respective height 25 35 and 45 So these are the forming stages and wall angles. Okay, if we use directly if we use the single stage, then this third figure is used, okay, directly 70-degree wall angle and 45-degree wall angle. And if we use two stages, so this last two figures, means 55-degree wall angle and 70-degree wall angle will be used. And if we use three stages, then these three figures, first stage, second stage, and third stage will be used. And here the response measurement means how the we measure we require output two, right, geometric accuracy and surface roughness. So how we measure this geometric accuracy of the component, or we can say part, right. So we have to use some laser scanner. We have to use some laser scanner, and then we can get the point cloud data. And if we fed this point cloud data in our SolidWorks software, right, then the comparison of scan and target profile can be done. Okay, so because so in SolidWorks, the part, if we design the part, so the target profile, we will obtain the target profile. Okay, and from this laser scanner, we 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 scan the whole component. Okay, so the uh, profile final profile of the form part we can obtain, and it will be converted to point cloud data, and then this point cloud data is fed to the SolidWorks software, and comparison will be done between scan profile and target profile. And before laser scanning, we use this spot check xkd s2 developer, right? uh, we use this developer, so the scanning will be done effectively. Okay, so that is why this here we can observe some white particles on the component, right? So using this uh, using this developer, the laser scanner can be scan the objects very accurately. Okay, so here the Dr. Pizza 3D laser scanner is used to scan the object, and here the comparison is done between scan profile and target profile. These are the form parts are scanned using okay, so how the statistical analysis, how we done the statistical analysis. So the difference in target profile and geometry part the part form part geometry is measured at 21 different points. Here you can observe this is the target profile, right? This is the target profile, and the inner region, okay, inner region is the scan profile. Okay, so here you can observe some difference between target profile and scan profile. Okay, so that is called the geometric inaccuracy. So here some points are we can observe some points. Okay, so at each points some values we can get xi and x some target values, observed values we can get. Okay, here target values xi and observed value x naught, right? So uh, the difference between target profile and form part geometry is measured at 21 different points. Okay, this is the 21 different points. Okay, and right side is also other 21 different points. Okay, so then this geometric error means we can say this difference between target profile and form part, it is converted into root mean square error, RMSE, root mean square error. So this is the equation for the RMSE. So this geometric error is converted to root mean square error. Okay, because what happened, sometimes your difference, okay, sometimes your difference will be on negative side, or we can say in positive side, right? So if we only done the some of these errors, right? So there are chances one positive and one negative error will uh, not give the any influence, right? Not give the any effect on the geometric error, right? So first of all we have to taken this difference, then do square, and then sum, do this sum, and using this RMSE equation we can get the RMSE value. This is the measurement of so this is the measurement of geometric accuracy, right? We can obtain the geometric accuracy. And this is the second one parameter, second output, surface roughness. Okay, so how to measure the surface roughness? So first we use the Mitutoyo surface SA310. Before going to this equipment, we have to check the parallelism of the part, right? So here spirit level is used to check the horizontal adjustment of the part. Okay, and then using this meter surface as a 310, we can get the RA values, right? Surface roughness is measured in RA, right? So that will be obtained from this surface as a 310 equipment, right? So these are the measurement, like methods of the measurement of geometric accuracy and measurement of surface roughness. uh, Here the process parameters, which parameters we have used, right? Feed rate, number of stages, pitch size. So these are the three important parameters we have kept, right? Feed rate, number of stages, and pitch size. uh, are you as we discuss here, a number of stages, right? Single stage, two stage, three stage. So these are the forming stages. So this is our important parameter. Okay. One of the uh, three parameters. This one is the important parameter, uh, number of forming stages. And second one is pitch size, right? Pitch size means delta z in vertical direction, how much the small incremental will go, right? So, and another is the feed rate. Okay, so these three input process parameters: feed rate, number of stages, and pitch size. And then the responses are geometric error and surface roughness. Okay, so these two are the our responses: geometric error and surface roughness. So how we measure this geometric error and surface roughness, we have already seen, right? Then this process, we use Taguchi's method for DOE, design of experiments, in which L18 orthogonal array is used. This will be done in Minitab software. Okay, Minitab 18.1 software. So using this Minitab software, and using some levels of the parameters, we can get the required number of experiments. Okay, how many experiments are required to analyze these two responses: geometric error and surface roughness, effectively. So we use this Minitab software in which Taguchi method is used, and the analysis is carried out using analysis of variance ANOVA. Okay, using ANOVA method, the analysis will be carried out. Here are the process parameters and their labels. DOE, design of experiments, process parameters and their labels. So for feed rate, two levels are used: level 1 and level 2, 2400 mm per unit and 3600 mm per unit. And for pitch size, there are three levels. In first level, 0.3 mm, second one 0.65 mm, and third one is 1 mm. Okay, so this is the delta z value, okay, in vertically downward direction. In first stage, 0.3 mm, in second stage 0.65 mm, and in third stage 1 mm. This pitch size will be carried out. Number of stages: single stage, two stage, and three stages. Okay. Process parameters, which are the kept constants. So these are the process parameters: tool diameter, wall angle, and all. So here we kept these process parameters are constant. This is L18 orthogonal array. So from Minitab software, we get these number of experiments, how many number of experiments required, then feed rate, number of stages, and pitch size. Okay. So in first experiment, 2400 mm feed rate, single stage, pitch size 0.3 mm, and goes on through till 18 experiment, right? So this is the formed part. Okay. Using multi-stage incremental forming. Okay. So these are the 18 parts, and their input parameters are here. Okay. What is the feed rate, what is number of stages, single stage, two stage, or three stage, and what is the pitch size is used. Okay, 0.3 mm, 0.65 mm, or 1 mm. So these are the 18 form parts are used. 18 form parts are processed, right? uh, Here you can see every part has some lines. Okay, vertically. Here the pointer, you can see this line, this line. Okay, this line. So here in this Cartwheel Mill software, you can see this line. Okay, so using this tool path, you can observe this line after the forming. Okay, but if we use the spiral tool path, okay, this line can be minimized, right? We can say eliminated. So these are the 18 parts, and these are the results and discussion. Uh, so this is also done in the Minitab software. Okay, means the RMSE value kept fed into the Minitab software, and these are the ANOVA analysis. Okay, so here feed rate, number of stages for each experiment, the RMSE value is measured, right? How we measure the RMS as RMSE value? Using this method, right? Response measurement, component spread, or after scanning, the Dr. Pizza 3D laser scanner is used. Then SolidWorks. In SolidWorks, the target measure the difference between target profile and scan profile, and then RMSE value we get, right? So here for each experiment, the RMSE value will be calculated, and then using ANOVA analysis, okay, analysis of variance using ANOVA, we can get the important parameters, right? Which parameter affect the most, right? So here some we can say statistical data, degree of freedom, sum of square, mean square. But the important parameters, important values are, first one is f value and second one is p value. Okay, so if the p value of the parameters is less than 0.05, okay, if we the p value is less than 0.05 mm, 0 point, is less than 0.05 unit, so that is the most important parameter, right? So here observe, we can observe the p value is less than 0.05 for two parameters, number of stages and pitch, right? So these are the significant parameters. And f value, this is the f value, right? So what indicates f value? If the f value is more, okay, compared to all other parameters, then that parameters will affect the most affect the parameters in our output response, okay, geometric accuracy. So here 69.27 value is maximum value for the number of stages, right? So number of stages means single stage, two stage, three stage has more influence on the geometric accuracy compared to other parameters. Okay, and feed rate has no, it is not significant parameter, right? So feed rate से उतना affect नहीं हो रहा है, right? So here are the graphs, effect of process parameters on geometric error, feed rate, stages, number of stages, and pitch, right? So here you can observe feed rate. So in these are the geometric error, right? 2.2, 2.3, 2.6, 3.1. Okay, so these are values are the geometric error, right? So here you can see from 2400 to 3600 mm per unit, the changes in geometric error are marginally lower, right? But using number of stages, you can say if we use single stage, the geometric error is maximum, and using three stages, the geometric error is minimum, right? So using when we increase the number of stages, the geometric error is decreasing, right? Or we can say we improve our geometric accuracy, right? And using pitch size, if we increase the pitch size, the geometric error is also increases. Okay, so from this graph we can clearly see that the if we increase the number of stages, the geometric error will be decreased, and if we increase the pitch value, then the geometric error is also increasing. This is the mathematical predictive model. This is the equation for RMSE. Okay, we can say regression equation. Okay, so this is the we obtain from the Minitab software. Okay, ANOVA analysis. We using these input process parameters, feed rate, number of stages, and pitch size. So we can calculate the we can predict the RMSE value. Okay, geometric error by giving some input parameters, right? So these are the observed and predictive values of RMSE. Okay, observed value RMSE and predictive RMSE using this equation, right? So this is the predictive model for the geometric accuracy. Then a measure surface roughness. Okay, so surface roughness is also measured. So these are the RA values. Okay, then investigation is also run using ANOVA analysis. Okay, and here we can observe p value less than 0.05 for both number of stages and pitch size, right? So both are the significant parameter, and for feed rate the value is not less than 0.05. Okay, so it is insignificant parameter, and from significant parameters, f value is larger for number of stages, right? 13.89. So that is the most important parameters which affect the surface roughness. Okay, number of stages has more important, it is the most important parameter. So this is the graph. Okay, feed rate, there is a marginally effect. Okay, number of stages, if we increase the number of stages, the surface roughness is also increasing. Okay, in geometric accuracy, geometric error will decrease if we use increase the number of stages. Okay, but here surface roughness is increasing using more number of stages, and using large piece size also the surface roughness is increasing. Okay, so this is the effect of process parameters. This is the mathematical predictive model cap obtained from the ANOVA analysis minute of software. So using feed rate, number of stages, piece size, we can get the we can predict the value of surface roughness RA. Okay, so these are the observed and predictive values of surface roughness. So these are the conclusions. First one is we have three process parameters, right? Number of stages, feed rate, and pitch size. So from these three process parameters, number of forming stages and pitch size have significant effect on the geometric accuracy. Okay, if we talk about the geometric accuracy only, so these are the two important significant parameters which affect the geometric accuracy. And from both parameters, number of stages is the most significant parameter. Okay, followed by which pitch size. Okay, for pitch size is also important parameter, but the number of stages is the most significant parameter. Okay, and if we increase the number of stages, the RMSE value decreases. Okay, and we can improve the our geometric accuracy, right? But using larger pitch size, poor geometric accuracy we can obtain. Okay, so we have to keep smaller pitch size. And if we discuss about the surface roughness, so if we increase the number of stages, both are important parameters, number of stages and pitch size. Okay, and feed rate is has insignificant parameter for surface roughness. So as the number of stages, if we both increase number of stages and pitch size, so surface roughness is also increasing, right? So this is the limitation of this our multi-stage incremental forming. If we increase the number of stages, the surface roughness also increases, right? So we have to maintain this relationship of the number of stages and require surface roughness and geometric accuracy, right? So we cannot use high number of stages. Okay, if we use more number of stages, the surface roughness also increases, right? So we have to make some uh, relation between geometric accuracy and the surface roughness and number of stages, right? And feed rate has no influence on surface roughness and geometric accuracy. So higher feed rate can be used, so forming time can be reduced, because this is the also limitation of the incremental seed forming. Why we not use in industrial, why this process is not used in industry? Because the forming time is very much high. Okay, but for small batch production, or we can say customized product or customized our components, we can use this incremental seed forming. So the future scope, in future scope, we can observe, we can form for non-axis symmetric parts using this multi-stage process. And We can study here only we studied on the aluminum material. Okay, so we can use the other materials like copper, steel, polymers, etc. using multi-stage. And as I told you, the spiral tool, if we use spiral tool path, the straight lines is not observed, so you can study on the geometric equation surface reference using spiral tool path. So this is the future scope. These are the references. Okay, I hope uh, you can learn about some knowledge, you have some knowledge about the incremental forming process. Manish,
Yes, Sunan sir. On behalf of Parallel University and Mechanical Engineering departments, I would like to
yes,
thank Mr. Sunan sir for informative and fruitful webinar and for sharing the grand knowledge with our students. And I hope that the students have learned so much things from that webinar regarding the incremental forming processes. And thank you so much, sir, for your precious time. Uh,
yes, most welcome.
yes, yes. Thank you so much, sir.
Is there any question, Manish sir?
Sir, if it is any question, then I'll text you. Till now, no questions from student side. If it is any
Okay,
question, then we will WhatsApp you.
sure, sure, no
Oh,
problem.
okay.
Okay, I'll left. Okay,
Yes, 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 yes. Thank you so much, sir.
okay.